A very warm good afternoon to all of you. I am Sakshi, welcoming you all on behalf of Solar Quarter and First View Group to Multiphysics Simulation for Solar Energy Applications. I take the pleasure to thank our speaker for investing her precious time to join the event, and a very special thanks to our partner Comsol for their immense support to help organize this event. For everyone here, there's a poll coming up, so kindly vote. The polls are open throughout the session. The polls will be open throughout the session. Uh, I would now request my team to play the promotional video for Comsol.
Developing designs and performing experiments virtually is both cost and time efficient. With COMSOL Multiphysics simulation software, you can be sure your results accurately represent the real world. By studying multiple physical effects on one model, no matter the order in which you combine different physics, the software handles them together and solves the mathematical and numerical model equations and provides you with the model results. The entire simulation process takes place in the same software environment. You only need to learn one workflow, no matter the physics involved or the nature of your experiments. Depending on the scenario, you may want to model single physics, one-way multiphysics, or fully coupled multiphysics. The COMSOL software offers all three, and the true advantage of COMSOL Multiphysics is the ability to model unlimited multiphysics, where all physics in a model interact, affect each other, and together influence the model results. If you need to add any physics, including your own equations, to your model, you can. The application builder in COMSOL Multiphysics gives you the tools to build your own simulation apps. The Startup Wizard and drag and drop functionality help you quickly turn your models into simulation apps with customized user interfaces, restricted inputs and outputs, report generators, and more. This way, you can spread the advantages of simulation to colleagues and customers by compiling your apps as standalone executables via COMSOL compiler, or by making them accessible by web browser via COMSOL server. Understand, predict, innovate, and optimize your processes and designs with COMSOL Multiphysics.
Thank you, team, for playing that video. I would like to welcome all of you to our exclusive live webinar, where we will delve today in the intricate world of designing robust and efficient solar energy infrastructure through the lens of multiphysics simulation. You might wonder why this is important. Well, the answer lies in the optimization of the R&D process. Multiphysics simulation empowers us to fine-tune every aspect of solar energy infrastructure, leading to enhanced efficiency, durability, and overall performance. This not only ensures that the designs meet the highest standards, but also significantly reduces the time to market, allowing us to bring advanced solutions to you faster than ever before. May I now introduce Ms. Kavita, who's the applications manager at Comsol. She will be sharing the presentation for her company. Uh, Over to you, Ms. Kavita.
Thank you, Sakshi. Good afternoon, everyone. So let me share my screen. Yeah. Very good afternoon, everyone. And thank you for showing interest in today's webinar that is presented by Comsol Multiphysics India team. Today, I will be presenting the capabilities of Comsol Multiphysics tool in multiphysics simulations for solar energy applications. So the design and development of solar energy infrastructure elements such as photovoltaic cells, solar panels, power generators, and transmission lines involve accounting for a number of different physics phenomena as well as operating conditions requiring the need of multiphysics simulation. For example, while modeling solar panel, we need semiconductor physics modeling to get higher efficiency for each solar cell. This efficiency not only depends on the semiconductor material but also on the placement and orientation of the solar panel in a given geographical location. See now at a given geographical location, will the solar panel withstand the wind load or not? Will it suffer with corrosion and erosion effects or not? All these external influences also affect the efficiency of solar panels, and evaluating the degradation of efficiency of solar panels due to external factor is very important, which can be simulated using COMSOL multiphysics software tool. Even for single physics, COMSOL multiphysics offers modeling in a very wide range of engineering and physics fields. This means engineers and scientists can utilize one modeling software for vast number of applications. In addition, the physics interfaces in all engineering and physics can be arbitrarily coupled, resulting in a unique suite of multiphysics modeling capabilities. So let me start with highlighting few successful user stories where solar industry has used COMSOL simulation tool in addressing their queries and issues. So one of our successful user story is from engineers of EMIX from France. The problem statement here was the engineers wanted to use multiphysics simulation to optimize the cold crucible continuous casting process for the manufacture of photovoltaic quality silicon wafers. So the main challenge they faced were they were interested in reducing the photovoltaic quality silicon wafer cost by improving the production efficiency. They also wanted to increase its purity. So to do so, multiphysics simulation was used to characterize several aspects of manufacturing process, including coupled electromagnetic effects and heat transfer. COMSOL multiphysics simulation was used to predict electromagnetic heating of the crucible and the corresponding phases of the molten silica. Also, they use multi-scale electromagnetic and 3D continuous casting simulations. The electromagnetic simulations permitted them to estimate inductance and impedance as well as the optimization of the crucible design to improve the electrical efficiency, whereas the continuous casting simulations allowed for the input of parameters such as the required electromagnetic power, crystallization rate, height of the crucible cooling zone, and after heat temperatures. The combined results of these studies have led to a compromise between high production rates and low stresses in the ingots. So to do this simulation, multiphysics simulation was used to characterize several aspects of EMIX manufacture process, including coupled electromagnetic effects and heat transfer. The next user story is from Italian utility ENEL and the Italian National Agency for New Technologies. They both joined together to develop a new kind of concentrating solar power using parabolic surface. Concentrating solar power plant generates electricity during sunny hours as well as under overcast conditions. This new type of concentrating solar power plant depends on molten silica as a medium for storing heat in large, well insulated tanks, replacing pressurized oil as fluid for heat transfer. Molten salt had several advantages over the previously used pressurized oil for them because it can operate at higher temperature, which maximizes the energy efficiency. So, keeping the salt in the liquid state presented a challenge for the team. They used COMSOL multiphysics and its built in library of heat transfer coefficients to analyze temperature and heat loss throughout the drainage circuit, optimizing both its geometry and insulation properties. So the two user stories that I presented here, they are from the existing users. But today, I would like to know more about the interest areas of today's audience. So I would like to launch a poll question here. I would also request Sakshi to launch the poll question from her end. So by launching this poll question, we would like to know whether you are interested in modeling solar cells at the device level, that is at the PN junction level, or you are interested in modeling the environmental effects on solar panel, or you are interested in modeling solar concentrators and solar cookers kind of application, or if you are interested in any other kind of application, please specify that in the chat window. So we'll give few more seconds. You can take part in the poll question. Okay, thank you. So let's move back to the session. Let me start with describing how multiphysics simulation can play a major role in addressing the environmental effects on solar panel performance. When a solar panel is placed in an open environment, it experiences wind load. Whether the solar panel can withstand the wind load or not, this question needs to be addressed, and here multiphysics comes into picture, where you are interested in modeling the fluid flow and at the same time the structural behavior due to the interaction of fluid flow. COMSOL multiphysics helps you address such a phenomena with the help of fluid structure interaction. Using COMSOL multiphysics, you can couple n number of physics together in unidirectional or fully coupled form. Regardless of which physics you solve for, the modeling workflow is going to be the same, and you can do everything in a single desktop user interface. Towards the end, I will take you through a quick demo on modeling this fluid structure interaction of a solar panel that is to be deployed in a solar farm. In addition to this, in an open field, wind also carries dust with it, and prolonged exposure of these moving dust particles or the sand grains with the solid structure, such as the reflectors of concentrated solar power plants, which are made of mirrors, leads to erosion of reflectors, resulting in diffusion of light and decrease in energy efficiency in solar power plants. The anti-reflective coatings in the glass panels used to protect solar PV are susceptible to erosion by sand particles carried by heavy winds. So therefore, estimating the rate of erosion due to these external effects can help understand the lifespan of solar panel facility in a given geographical location. So this kind of erosion modeling is also possible with COMSOL multiphysics tool. Also, the metallic solar panel support structures in long run lose their strength due to corrosion, and thus predicting corrosion rate and taking preventive actions can increase the life of the deployed system. With COMSOL multiphysics, using the corrosion module, you can identify the corrosion rate by modeling the corrosion process, and you can also model different types of corrosion protection systems. Well-defined physics interfaces are available in COMSOL to model the corrosion phenomena as well. In addition to the topics that we discussed, there are also many other applications that can be modeled using COMSOL multiphysics related to solar power. One such application is solar concentrator. The photovoltaic devices are already a standard for some off-grid and on-grid application, and their usage in other areas is increasing. In combination with concentrated solar technology, they will play a central role in the future of world's electricity. So, a paraboloid dish concentrator can focus incident solar radiation onto a target or cavity receiver, resulting in very high local heat fluxes. This can be used to generate steam, which can be further used to power a generator, or it can be used to generate hydrogen, which can be used directly as a fuel source. So, for modeling the solar concentrator, ray tracing phenomena will be required, where we will consider solar energy in the form of rays. We can track those rays whenever they are incident on the parabolic surface. We will consider the thermal effect. We can apply appropriate boundary conditions specifying how the rays will interact with different boundaries, whether they will undergo specular reflection, diffuse scattering, or absorption. In order to use appropriate materials, we also have a wide list of material library. So in the right top corner here, let me choose my pointer. So in the top right corner here, you can see that by considering the surface roughness on these parabolic surfaces, how the concentration ratio is reduced drastically when compared to an ideal smooth reflector surface. So these kind of simulations can be performed using COMSOL tool. As we are concentrating solar energy, addressing the heat transfer mechanism also becomes important. Here, the radiation phenomena is predominant, where you need to consider surface to ambient or surface to surface radiation phenomena. In addition to radiation mechanism, you can also model conduction and convection type of heat transfer phenomena with COMSOL multiphysics, and it can also be further coupled with flow simulations such as laminar and turbulent flow. Let me show you here another example that is closer to a solar cooker application. This example model from the application gallery of COMSOL illustrates the greenhouse effect in a box covered by a plate and exposed to sun's radiation over a day. The bottom image shows you how the temperature varies in the box and the top plate throughout the day with respect to the location of the sun. The temperature variation is monitored in two cases with a plate made of glass transparent to solar radiation and opaque to ambient radiation. Because of greenhouse effect, there will be rise in temperature. So these kind of simulations are possible in COMSOL. So to model the phenomena that we discussed in the previous slide, we need to consider the surface to surface radiation. You also need to specify whether the surfaces are diffusive or specular again. You can also reduce the geometry complexity by using symmetry planes or sector symmetry. In COMSOL multiphysics, a ready-made interface is available to model the surface-to-surface radiation, where you can apply the surface properties in two different sides of a boundary. That could be emissivity, density, etc. You can also consider specular and semi-transparent properties for your boundaries. So the user stories and the examples that we discussed here help us understand the importance of multiphysics simulation in solar application. Solar panels are essentially the arrangement of solar cells, which are PN junction diodes. Now, a fundamental question arises: can we model the solar cell at device level? Let us take a quick dive into semiconductor modeling, which can be offered by COMSOL multiphysics software. In semiconductor physics interface, we solve for combined drift diffusion equations for electrons and holes along with Poisson's equation. You can define different doping profiles and define different generation and recombination rate for the electrons and holes. So let's take an example where we are modeling the solar cell at the semiconductor level. Doping profiles are defined for semiconductor modeling such as the donor and acceptor concentration as shown in the top right corner. You can also consider different recombination and generation rates. So this is the screenshot of COMSOL desktop interface. I will also in detail explain the desktop interface when we do the demo. So here I'm showing the screenshot to address this example of modeling a solar cell. So irrespective of the physics, the workflow is going to remain the same when you are using the COMSOL tool. So first you will be defining the parameters that you require to model your geometry. Then you model the geometry. Then you assign materials to the geometry that you created. Then you set up as many number of physics that you want. Here in this example, it's semiconductor, but you can add as many number of physics in the same desktop interface. Then you mesh your geometry. Then you perform the study. You simulate and perform the study, and you can visualize the result. So COMSOL follows the top-down approach for the modeling workflow. And any type of physics that you solve for, you will be using the same modeling workflow in the same desktop. So here the semiconductor physics interface shown here basically solves for the drift diffusion equation along with the Poisson's equation. So in COMSOL, the beauty of the COMSOL is any physics interface that you are going to use, you can visualize the equations that you are solving for. And also if you are setting up different boundary conditions, and you can see the equations that you apply at those boundary conditions, everything can be visualized. So here in the semiconductor physics interface, so here in this example, we have considered complete ionization for the dopant. Here we are considering the Fermi-Dirac distribution to consider the concentration level, and we solve for the electron and hole pairs. In the physics toolbar, you can choose the analytic doping model for the domains, and we choose donor doping as N-type from the impurity list. Then you can add Gaussian doping decaying away from the surface of the device to form the PN junction. The geometric doping model is convenient for setting up this kind of doping profiles. Next, here you can also define the acceptor doping concentration. So when the sun rays falls on the PN junction, they are going to generate electron-hole pair. With the help of trap-assisted recombination, the well-known Shockley-Reed-Hall model, we are considering the electron lifetime and hole lifetime. The generation rate depends on the material properties that you choose. Then you define the user-defined generation rate for the electrons and holes. Then you apply the biasing conditions using the metal contact boundary condition. Here you can see the variable used to define the generation rate, which is a function of solar spectrum and a function of silicon's absorption spectrum. The solar spectrum is defined as an interpolation function. So if you have the material properties as a function of frequency or wavelength, you can import those material properties. So for solar spectrum, here we can define it as an interpolation function as provided by the solar cell manufacturer. Also, the silicon's absorption spectrum is also defined as the interpolation function. And after completion of defining the physics boundary conditions, you mesh the geometry using the mesh node and perform the stationary study for different biasing voltages. And then you visualize the results. Here in this example, you can see the maximum power is almost generated is almost 16.7 milliwatt. You can also plot energy diagram, carrier concentration, recombination, and generation rate. So this is about modeling of solar cell at semiconductor level. So now let me take you through the demo on modeling fluid structure interaction of a solar panel that is going to be placed in a solar farm. This example is a study of solar panel structure placed in a periodic flow field. The solar panel to be simulated for is located inside a regularly spaced array of panels subjected to an oncoming strong wind. This model solves for the flow around the panel and the structural displacement due to the fluid load. So let me navigate to the COMSOL session. So when you open the COMSOL session for the first time, this is the window that you will be taken into. So we have two ways to enter the desktop interface. So you can choose model wizard or blank model. Model wizard is the recommended approach where you will get to know the different types of physics that can be solved and what are the physics interfaces that you have to choose and what types of studies are available for the physics interfaces. So this will be a guided approach. So the recommended approach is the model wizard. Let me choose the model wizard. And once you choose the model wizard, here you will get a screen where you can select the space dimension, whether you want to model in 3D or you want to model in 2D, or if you are going to have axis symmetry in your models, then you can choose 2D axis symmetry. So in our example, we are going to model in 3D. So let me choose 3D. And so you can ignore the recently used. So here you will be listed with the different physics that are available. So it will depend upon the modules that you have installed in your computer. So here in our example, we are going to model the fluid flow for the air flow or the wind flow around the solar panel. So let's choose first the fluid flow, and we are going to have the single phase flow and turbulent flow, and we are going to model the turbulent flow K epsilon. We are going to use this physics interface. Let me choose add. So as I told, you can solve for single physics or multiple physics, n number of multiple physics together to have a couple simulation, and your coupling can be unidirectional or fully coupled. So here it is a couple multiphysics coupled simulation. So the wind load is going to apply the stress on your solar panel. So we also need to include the stress effects. So we will choose the structural mechanics, solid mechanics interface. I'll click add. So now two physics interfaces are added since I'm going to solve these two physics. So if you want to add more, then you can go and keep adding more number of physics as required for your application. Then you can click study. So for each physics that you choose will have different types of study. So the primary studies in general will be stationary study or time dependent study. And also you will have other studies based on your physics interface. So these both are the general study. So we will use the stationary study and click done. So this is the COMSOL desktop user interface. So you have three main windows here. Towards the left, you have the model builder. Towards the right, you have the graphics window where you can visualize your geometry, mesh, and the results. And in the bottom, you have the information window where you can see the progress of your simulation logs, or if you want to evaluate the results in the form of table, it gets displayed here. And also you have a settings window. So if you are going to set up your model using different nodes in the model builder, so each node will have the appropriate settings displayed in the settings window. And also you have a top ribbon tab. The top ribbon tab and the model builder serves the same purpose. They are going to guide you through the modeling workflow. So you can use the top ribbon tab to model your application, or you can use the model builder. So if you see the model builder, it follows the top-down approach as I mentioned here earlier. So first you will define the parameters required. So you can start typing the parameters here, or you can load the parameters from a file. So let me example, I'll just show you. So you can load it from file, or you can write down your parameters to model the geometry, or parameters that will set up your physics boundary conditions. Then you create the geometry, then you assign materials, then you set up the physics. So here we have told which physics interface that we want to include. Furthermore, you can also keep adding in the same window. You can right click and choose add physics, or you can go to the physics tab and you can add as many number of physics that you want. You can define the multiphysics. So in our example, so we are going to have two physics, so we can check whether already we have a predefined multiphysics. So we have a fluid structure interaction, so we can use this multiphysics node. Then you measure geometry, then you compute your study, and then you visualize your result. So this is the modeling workflow. So to create the geometry, you can right click and use different geometry primitives that are available, or you can import your own geometry from any CAD tool. And also you have the flexibility to import geometry in form of mesh file. You can also import your geometry in the form of mesh file. So let me open the console window where I have the geometry imported. So here I have imported a mesh file which represents my geometry. So we have assigned various materials: air, structural steel for supporting structures, aluminium, and glass for the solar panel. Then we have two physics interface here, as I had told earlier. Now we'll see an example how to set up one of the physics interface. So any physics interface that you choose, I had mentioned what are, you can see what are the equation that you are going to solve for, whether it is turbulent flow or even the solid mechanics. Any physics interface that you're going to use, you can visualize the equations that you solve for, and also for all the boundary conditions that you apply, you can also see the equations that is solved behind. So here in this example, we are modeling a unit cell, and this solar panel is going to be periodically placed in a solar form. And also we have included only half of the panel structure instead of the full panel. Only half of the geometry is included, so we can also use the symmetry condition to save on computation. So since we are modeling this for a periodic problem, so we need to have the periodic flow condition. So let me apply a periodic flow boundary condition. So here the periodic flow is going to be in XZ plane. So this node will specify the pressure difference in the streamwise direction, which is the XZ plane here. So let me add the periodic boundary condition, periodic flow boundary condition. Then on the top, we will have an open boundary to specify the stresses. So you can choose the open boundary. And the solar panel is symmetric about the streamwise plane through the center of the structure. So you can include one half of the geometry and apply symmetry boundary conditions in the lateral directions. So you can right click and choose symmetry boundary condition for the lateral directions. So almost this physics interface is set up, and you can also include the pressure difference using the ordinary differential equation or ODE and DA interfaces. Then you can set up the same way the solid mechanics physics interface. So you can mention the fixed constraints. So where you want to apply the fixed constraint for the solar panel structure, say here when you want to compute for these stresses, so where you want to have the constraints fixed. And here also you include the symmetry boundary conditions at the appropriate boundaries. Then you set up your multiphysics simulation. So here we saw that The turbulent flow is going to solve for the turbulent flow around the solar panel using the turbulent flow K epsilon physics interface. And the other interface is going to solve for the structural stresses and displacement due to the fluid load that is computed from the turbulent flow model. The multiphysics coupling feature fluid structure interaction fixed geometry. This will be used to couple the fluid flow boundary load from the fluid domains to the solid domains. So this corresponds to a one-way fluid structure interaction analysis. But in case if you want to have fully coupled, then you can also use fully coupled simulation. Already this is a mesh file. In case if you have created the geometry, then you can use the physics control mesh to mesh the geometry, or you can go for the user control mesh where you want to specify more refining for your structure. Then you do the first study, which is the stationary study on turbulent flow physics interface. Then you perform the study for the solid mechanics to solve for the stress and displacement due to the wind load that was computed using the turbulent flow physics interface. So you can also specify that values of variables not solved for that you want to choose it from the previous solution that you have computed using the stationary study that you have done in the turbulent flow model. So here the wind load will be applied in the solid mechanics model, and you will be computing the stresses and displacement. So once you are done with setting up the physics and setting up the study, then you will click compute to evaluate the result. So just to save time, let me open a model where I have the results evaluated. So you can visualize different. So this is the same model that I had discussed earlier. So you can see we have the turbulent flow interface setup and the solid mechanics. We have the multiphysics and we have both the studies here. So you can visualize the velocity profile. You can visualize the pressure that is exerted on your solar panel. You can have the streamlined plot of the wind flow. You can plot your stresses in the form of stress or displacement. Here you can see the stress and displacement due to the wind load. You can also further visualize the safety factor for the ductile materials as well as the glass material. So this is just to give a quick idea about the COMSOL desktop interface and how you set up different physics, how you can couple multiple physics, perform your simulation and visualize the result. So let me go back to the presentation. Okay. So until now we saw the modeling of application using model builder. Here modeling and simulation involve specialists in mathematical modeling who are experts in a relevant physics or engineering field. Their work reduces the need for physical prototypes and yields better result in less time, creating significant value for their organization. But for research and development, apart from the team who is involved in simulation, there are also several other teams who play a crucial role. Here the use of application builder comes into picture. Here modeling specialists can create custom simulation apps based on their model, thereby bringing the benefits of multiphysics modeling and simulation to a larger group of engineers and scientists. Each model designed can be converted into apps and can be distributed with various teams where they can play around with different input parameters and control parameters and visualize the effect of parameters for the given model. So you can give the access of the simulation or give a feel about the simulation to field technicians or also the higher officials when you want to present your ideas. So, in addition, everyone can give feedback about the models to cover relevant operational ranges or even validating the models to improve the models further. Therefore, the application builder, the unique feature of COMSOL is going to make the collaborative works very effective and enhance the speed of design process by getting suggestions from various teams by circulating the apps. So one example shown here is a solar cell, a app for the solar cell. So let me actually take a quick guide through one of the app, which is this app itself, modeling the solar cell. So even the previous demo, we saw that we were working in the model builder using the model builder. So here in this example, where we are modeling the solar cell with ray optics. So what we are doing is we are actually going to give incident solar rays using the ray optics or the geometric optics physics interface of the ray optics module. So you can specify the solar radiation in terms of coordinates or choose the city at which day of the year, at what time you want to perform the simulation. So appropriate solar rays will be shined over your solar cell. And for semiconductor modeling, so you can model your solar cell at the semiconductor level. So let me switch to the application builder. So once you create any application using the model builder or you design any kind of application, you can always create apps out of this application, which you can circulate to people who don't have COMSOL being installed at their end. So let me navigate to application builder. So here the application builder is already set up for this example. So using the application builder, so here you can have different outlets created for your application using forms, various forms. You can also write your own set of codes using methods in case if you want to extend your physics interface further. So that is also possible. So where you can write different set of lines. Then once you set up, you can also test your application. Okay, the application is open. So this is the application. Only the selective inputs and outputs of the model are considered for the application. You need not consider all the input and output parameters for the application. So which are the parameters of importance can be included. So you can specify here, you can choose between different city coordinates. You can specify the date and year. You can specify the altitude above sea level. So you can have different input parameter sections. So one section here for sunlight properties and you have another section for cell properties. So you can specify how your solar cell is going to be oriented. Uh, so you can specify the azimuth angle and the cell tilt angle. So this will depend on the geographical location, how you want to orient the solar panel. Then you can have different studies, like you can change the parameters here, and again you can run your app. You can visualize different results. So here the sun's position is shown. So you can also visualize different results. So this kind of application will be very useful when you want to have a collaborative work and get feedback from other teams. Say in this example, you have designed solar panel and you want semiconductor team to have a look at the cell properties and how the cell properties is affecting the efficiency. So then they can have a look at the app by changing the properties, what is happening, and they can provide feedbacks how to improve the model. So this is one of the unique feature of COMSOL where you can create app out of your application that you built. So let me go back. So to conclude, in COMSOL multiphysics, you have a wide range of functionality for modeling of solar cells, solar irradiation, heat transfer, corrosion, fluid structure interaction, and hence you have unique capabilities for multiphysics modeling of real-world solar energy system. So with this, we are now open for the questions, and before the questions, I would also request Sakshi to launch the last poll question. So this will help us know like how you want to get connected with COMSOL further. So everyone can take part in the poll question. And further to proceed, we are open for questions.
Thank you so much for that insightful presentation, Ms. Kavita. We would like to now screen questions and inquiries from the audience for the speaker here. Um, Kavita, if you could elaborate on this.
So I
Kavita,
think
yeah.
uh, so the question or the information required is whether we can simulate environmental effects on solar panel. So this is what is displayed. So yes, you can simulate the environmental effects on solar panels. So this was the one of the important area that we wanted to address today. And yeah, so that was what the demo was also about. So and this is one of the main area that we will be covering, because when you have to include the environmental effects on solar panel, that's when multiphysics is going to come into picture, and where COMSOL is going to play a major role or a very good role in modeling the multiphysics simulation. Yeah, as I mentioned, you can like simulate for different environmental phenomena, like such as how corrosion or erosion is going to affect the glass panels of these solar panels that is going to deployed in a farm, or even a single solar panel, how the efficiency of the solar panel is going to get affected with the environmental effects, and what type of material changes that you can include, and how further you can make like your system more stable and robust. So for that environmental effects, taking the environmental effects during the design of the solar panel as well as the mounting structure for the solar panel is going to become very important.
I believe our topic was entirely based on this question itself. Kavita, would you like to elaborate on the same and give your closing remarks?
Yeah. So there is another one question related to simulating cell for best outdoor performance. Yes, so this was also one topic that we had taken today. So we wanted to see how real time we wanted to launch the solar rays and see the efficiency of the solar cell at efficiency of the photovoltaic cell at the PN junction level itself. We wanted to have the efficiency in terms of how much power is generated with respect to the voltage. So we saw one of the application today, and we also saw the app that I had taken a quick demo of the app. So that app is mainly based on this question: how to simulate solar cell for best outdoor performance. So here you use the ray tracing or the ray optics geometric optics interface, where you can launch the solar rays based on a coordinate. So based on the time and the location and the date, so you will have the solar rays or what is the solar intensity that you will have getting shined on the solar panel or the solar cell itself. So then you can model the single solar cell using the semiconductor physics interface, where you can model the PN junctions. Then you can get the efficiency and different kinds of results where you evaluate the performance of the PN junction diode.
All right, great. So I believe this is what we have for today. Anything else that you would like to add, Kavita?
Yeah, from my end, that is done. So one more time, maybe I would like to stress that COMSOL multiphysics. So the best thing with COMSOL multiphysics is you can couple n number of physics together, and you can have a couple simulation to model a real world scenario. So that's the beauty of the tool. And you will be doing that in a single physics interface. You will use the same modeling workflow for any physics that you solve for. So that's from my end. And I thank everyone for showing interest in today's webinar.
We have another question for you. We would like to get Miss Shilpi Sheetal on the stage for this. Hi,
Can,
Shilpi.
hello. Thanks a lot, because this is exactly what we have been thinking for quite a couple of months. So you actually did it for us. Thanks. One thing, can we have a trial license, please? Because we don't have all the modules with our license now.
To add on that, our marketing team or sales team will get back to you. So
Okay.
you can have the, if you do not have a specific module, you can have a trial license, and the marketing and the sales team will get back to you on that. Yeah.
Yeah. Thank you so much.
Thank you.
Thank you so much. Maybe Kavita, you can leave your details in the chat section here. Your email ID or your company's representative's email ID, so that our audience can connect with them in case of any networking queries. And with that, we have almost come to the end of the session. Very big thanks to our esteemed speakers, to our esteemed speaker, Ms. Kavita, for this wonderful session. Uh, a very big shout out to our attendees for extending their time and support for this event. Not to mention, not to forget our partner Comsol for extending their immense support to help organize this event. We'll be back with more exciting sessions soon. The floor is now open for networking. Thank you so much, everyone. Thanks.
Thank you.